All right. Hello, everyone. Welcome to the MIT Mobility Forum, organized by the MIT Mobility Initiative. I'm Jinhua Zhao, Professor of City and Transportation at MIT. Today, I'm really excited to have Professor Marco Pavone from Stanford join us today, talking about how to rethink the autonomous vehicle development with the foundational model. If you look at what happened in the past, like 12 months or so, one significant change is the foundational model trained at internet scale data set become really a new paradigm, moving from a domain-specific model development to this generalistic model and develop the broader common sense reasoning. It has demonstrated amazing performance in perception, in understanding, in creation, and also expanding to a multimodal to not only have a large language model like ChatGPT, also have a large visual model and a large action model. On the other side, if you look at autonomous vehicle industry, so we basically have two settings. One is the ADAS, mostly everywhere, everybody, or the driverless, but in a very limited ODD. The long discussion with this long tail problem keeps coming. So humans deal with this with a lifelong experience, use the common sense to deal with this uncommon phenomena, right? So here, can we really bring the two together? I think really excited to have Professor Marco Pavone to look at how will foundational model change the way we develop and deploy AI, and how can we generalize to the unseen here, right? So before I formally introduce Professor Marco Pavone, I do want to do some quick warm-up exercise. The first one is a quick poll here, if you can see. I want to get a sense of to what degree people are involved in AV development, right? I put it at several levels. One is direct involvement. I put it into two parts. One part is you're looking at the development of the machine itself, the AV technology per se. The second one is I'm looking at how the machine can be embedded in the broader transportation system in the sense of system design, consumer behavior, business model, insurance, public policy, etc. And then the next one, indirect, or the third one is just curious about it. All right, so I'll wait a few more seconds for people to participate. We have about 100 more people, 113 people participating. All right, so 123, I'll end the poll and share the result. Marco, maybe you can see about 18% about technology development, 33 in this more broader system design, 20 on the indirect, and 29 just curious. Cool. All right. So that's the first thing. The second thing is I will invite everybody to type into the chat your organization, your local city, and time. So I will say MIT, Cambridge, MA, 12, no. Right. So again, we'll get a sense of the audience here. I see it's international. Cool. Thank you. While we are doing this, let me reiterate the norm of this forum, which is I hope that everybody can contribute one idea, either in the sense of a comment to Marco's presentation or a question. Please type them directly in the chat. Right. Dr. Marco Pavone is an associate professor of Aeronautics at Stanford University, where he directs the Autonomous System Lab, ASL, and the Center for Autonomous Research at Stanford. He's also a distinguished research scientist at NVIDIA, where he leads the autonomous vehicle research. So it's really interesting that Dr. Pavone strutted both the academic and the industrial world. That's where I think the most exciting thing is happening here. Before that, he was a research technologist in the NASA JPL, the Jet Propulsion Laboratory. He, of course, is an alum at MIT, received a PhD degree from MIT in 2010. In terms of research, he develops the methodology for the analysis, design, and control of autonomous system, with a particular interest in self-driving cars, autonomous aerospace vehicles, and future mobility system. He received numerous awards. I just mentioned a few. One is the Presidential Early Career Award for Scientist and Engineer from President Barack Obama, Office of Naval Research for Young Investigator Award, also identified by American Society for Engineering Education as one of America's 20 most highly promising investigators on the age of 40. So without further ado, let me pass the forum to Professor Pavone. Marco, please.
Thank you very much for the introduction. It's exciting to see such a diverse audience for this discussion and this talk. So as mentioned in the introduction, in this talk, I'll discuss how foundation models such as large language models or vision language models provide the key opportunities to rethink how we develop autonomous systems and in particular autonomous vehicles. Now, the premise of this talk is that generative AI is changing the way we work and we seek out knowledge. For example, models can write code for us, as shown on the left. And the emergence of such capabilities is so profoundly revolutionary that some refer to it as the iPhone moment of AI. So it is natural to wonder what has been causing such an acceleration in the field of AI in the past year or so. Well, broadly speaking, what has happened is the advent of foundation models, which have shifted us from a paradigm of machine learning for specialized tasks towards more general knowledge acquisition. To be more specific, following a definition by the Center for Research on Foundation Models at Stanford, by foundation model, I mean a model that is trained on a broad data, typically at internet scale and in a self-supervised fashion, and that can be adapted to a wide range of downstream applications. Examples of foundation models include large language models, vision language models, and video generation models. NVIDIA actually has a catalog online of ready-to-use foundation models that you can test out interactively. Now, we're not quite yet at the level of one massive model that can consume any data modality and be adapted to any application. But this general approach of pre-training on a diverse data at massive scale and then fine-tuning to a given task has proven extremely powerful and often leads to the exclamation, wow, I had no idea that the model could even do that. So it's tempting to say AI, and in this case, a generative AI, makes everything better, so let's apply it to autonomous vehicles. Well, before applying foundation models to AV development, it's important to contextualize in what ways foundation models can boost AV performance and safety. We don't just want to jump on the bandwagon because there is a lot of hype about foundation models. And indeed, the AV technology is already quite reliable, at least in a specific operational design domains, with a very advanced ADAS system, automated driver assistance systems, being productized as we speak, and a remarkable progress being made by Waymo and others with deploying self-driving cars as a service. And this has been powered by the judicious incorporation of specialist machine learning models within the AV stack and the AV program. However, this system still missed the mark when exposed to the long tail of everything that could possibly happen out there on the road, which comprises new deployment domains, like, for example, new weather conditions or new cities, optical illusions such as traffic lights on a track, and other strange scenarios like the one in the bottom right, where there is, I don't even know what that is, a giant inflatable minion on the road. So these are all strange scenarios that require a higher level of semantic reasoning for generalization. At this point, it's useful to wonder how humans navigate the long tail. Well, as humans, we bring in a lifetime of general experiences beyond only driving, which enables stronger contextual and semantic understanding to reason about the long tail of events. Analogously, the hypothesis is that the foundation models, which have been trained on multiple lifetimes of very diverse data, both in the driving and crucially in non-driving domains, provide an opportunity to bring this outside information to the task of driving, thereby equipping next-generation AV stacks with the understanding and reasoning capabilities needed to navigate the long tail. At least, this is the hypothesis. Now, the question is how can we access this generalist experience for AV applications? And the answer is, in my mind, in multiple ways. As I'll discuss in the rest of the talk, foundation models, through their long-tail generalization capabilities, can empower several aspects of AV design and development, from improving offline development processes, such as auto-labeling, simulation, and scenario generation, all the way to drastically improving driving performance, either by enabling novel, more performant driving architectures, or by enhancing driver assistance systems. In other words, and this is a key point, foundation models provide opportunities to empower the full AV program. Of course, safety is paramount, and the common concern is that the foundation models might not be safely fielded in a safety-critical system such as an autonomous vehicle. And I will briefly discuss how we actually have several tools to keep foundation models in check. At the same time, I discuss how foundation models can also provide opportunities to increase the safety of an AV stack, for example, by enabling the design of semantic runtime monitors. So in the rest of the talk, I'll discuss a few examples from my research at NVIDIA and Stanford of how foundation models can be used in a variety of ways as part of an AV program, with an emphasis on vehicle applications. Now, let me start with the topic of simulation. Now, simulation is in many ways the holy grail for the development of autonomy stacks. And today we have technologies to realistically render driving scenes or to produce high-fidelity traffic behaviors. However, creating such simulations typically requires a lot of manual work in terms of tuning parameters or defining layouts to generate specific scenarios of interest. And this is an important setting where foundation models can boost our existing capabilities. Specifically, we have explored how large language models, or LLMs, can enable a new and intuitive interface to controlling the generation of simulation scenarios. With our recent work, LCT-Gen, we are able to not only control the evolution, but also the initialization of the simulation scenario via natural language descriptions. And here we can see the various iterative changes that a user can make to an initially generated scene. Interestingly, in the rightmost example, as we ask the model to speed up the different cars, the generation process is intelligent enough to move the blue vehicle to the right to avoid a collision with the red vehicle. So the generation is really dynamically informed. We can even seamlessly use outside sources of information, such as text-based crash reports, to generate plausible scenes that stress test AV stacks with scenarios extracted from real accidents. Here are a few examples where we reproduce real-world accidents described in the NHTSA siren database. So now we have a capability to ground simulations, for example, in police reports. So this is very exciting because it gives us a way to improve the realism in the scenario generation process. Just a little bit more in detail, LCT-Gen works by first converting a given scenario prompt into a structured representation, a detailed example of which can be shown below. And this representation is then taken as input into a map retrieval framework that selects the best fitting road layout from a data set of maps, as well as a motion generator, which places agents on the map and forecasts the motion for the next 5 seconds. So by coupling recent results from my group on neural rendering of dynamic scenes with the capability of generating targeted scenarios via language guidance, we can now simultaneously simulate sensor and human agent behavior in novel, targeted ways. For example, here, we can test an AV stack on a long-tail scenario whereby a vehicle shows ignorance of a stop sign. Specifically, in the original scenario, the vehicle stops at the stop sign. So this is the bottom row. So this is the camera log of a real scenario. Instead, in the modified rendered scenario, at the bottom, the vehicle ignores the sign and crosses the intersection with high speed. This opens the door to the holy grail in AV development, that of enabling a closed-loop evaluation and training with a minimal sim-to-real gap. For example, it's hard to tell that the scenario at the bottom is completely recreated in a simulation with the text as the interface. So it's exciting, but equally exciting is how we can use foundation models for the purposes of improving on-vehicle driving stacks, which is the next topic that I want to cover. In particular, as discussed at the beginning, foundation models hold the promise to allow us to drive better through more generalizable reasoning. But do we have evidence for that? And we recently explored two methods for using large language models and visual language models for driving, and both confirm that there is potential. On the left, our recent work, Agent Driver, treats large language models as embodied agents that loosely replicate how humans drive. It is leveraging capabilities on demand like detection and prediction, cognitive memory, chain of thought reasoning, and so on. And these different modules are orchestrated by the LLM agent through text as a unifying interface, calling the different modules on demand. Remarkably, this rather straightforward embodied pipeline enables a few-shot decision-making, which achieves a state-of-the-art performance. On the bottom left, we can see that a model that is trained with only 1% of the training data surpasses the previous state-of-the-art model, UniAD in this case, trained on 100% of the data. And there is no magic here, so the reason why we can achieve the result is that through the LLM, we leverage a generalist experience to the task of driving. So we need much less data in order to fine-tune the model to the task of driving. So Agent Driver only uses a large language model. In a separate work, namely Dolphins, we have explored how to use vision language models directly for the purposes of autonomous driving. And we got similarly encouraging results. Now, as mentioned before, the previous studies are primarily scientific explorations aimed at understanding the potential of using foundation models directly as part of the AV stack. And the studies do not really address implementation issues, for example, speed of inference for the large language models, or safety, for example, the potential of having hallucination in the generation process. We discuss safety considerations later in the talk. Here, I just want to mention that while foundation models are typically too large for direct implementation in embedded platforms, recent advances in shrinking and accelerating these models have made the infusion of adapted foundation models within an online AV stack a real possibility. In particular, such advancements have recently enabled deployment of foundation models such as Llama on embedded platforms such as Orin. Specifically, here we can see gains in inference speed when compressing models via a particular quantization method, enabling significant speedups without sacrificing performance with a Llama model on an Orin platform. Now, we have seen how foundation models, at least conceptually, can improve the task of driving and argue how they could be amenable to real-time inference on embedding platforms. So this motivates us to explore best ways to integrate them into a fully fledged AV stack. And that brings us to one of my favorite topics, that is that of system architecting. AV stack architecting is indeed a topic that has seen a resurgence of interest in the past few years. And before diving into the integration of foundation models within AV stacks, let me provide a bit of context about the two main paradigms for AV architectures. In the top left figure, we see a highly modular AV architecture, whose main components include perception, prediction, planning, and control. This is the most classical stack, and the key advantages of this architecture include interpretability, reusability, and debuggability. These are all very desirable properties, and this is one of the reasons why this architecture is still today very popular. However, this architecture introduces information bottlenecks. It's typically not end-to-end optimized and might give rise to integration challenges when you put everything together. In the top right figure, we have a monolithic style of end-to-end architectures, which directly links sensor data to control, typically through a neural network, and only implicitly encode key capabilities such as perception and prediction. As a key advantage, this monolithic architecture can be end-to-end optimized to, at least theoretically, achieve better performance. However, this architecture might give rise to interpretability and debuggability issues, and reasoning about its safety also poses a challenge. Interestingly, the advent of new differentiable algorithms along with new optimization techniques have recently led to the investigation of differentiable and modular AV stacks, an exciting new research direction that combine the best of both worlds. And to explore this direction, it's important to recognize that in the context of modular and differentiable AV stacks, the design space is huge. It encompasses, most importantly, the choice of modules, the choice of representations, and the dependency among modules or equivalently module placement. Prior work has generally focused on the first two directions, namely the choice of modules and the choice of representations. For example, for mapping, is it better to use a semantic BEV map as your representation of information, or maybe vectorized polylines and polygons? This is a design choice. Which one is best? Complementing this line of work, we have recently explored the third aspect I mentioned earlier, namely that of investigating dependencies among modules. For example, should occupancy prediction explicitly depend on motion prediction? As we will see shortly, this consideration will become important in terms of deciding how to best integrate foundation models within an AV stack. To systematically explore the huge design space along all three dimensions, in a paper that will be soon presented at CVPR, we propose a computational graph framework to model the general driving task. Given this framework, to reason about the necessity of a given module, we can simply observe the change in driving performance when adding or removing one node in the computational driving graph. To reason about module placement and corresponding dependencies, we can change the connectivity of edges in the graph and shuffle dependencies among modules. This can produce either fully sequential architectures or hybrid sequential parallel architectures. Additionally, we implemented the different edge types between modules, which stand for different data representations, such as latent features or interpretable outputs. Therefore, one can choose to connect different edges to explore the choice of representations for AV architectures. I'm quite excited about this work, as it provides one of the very first tools to systematically explore the design space for AV architectures. And thanks to this framework, we were able to conduct extensive experiments. And our key observation is interesting and also somewhat surprising. It turns out that, according to our analysis, the simplest design, namely a fully parallelized AV architecture, appears to be the best one in terms of both performance and efficiency. Briefly, this architecture, dubbed a ParaDrive, para stands for parallel, entails a transformer that takes multi-camera images as input and produces outputs in parallel for 4 core AV tasks, namely mapping, motion prediction, occupancy prediction, and motion planning. Importantly, ParaDrive follows the principle of train heavy and infer light. In offline training, all parallel heads are necessary and crucial, as the co-training of the different heads ensures that the learned features implicitly encode mapping, the notion of mapping, prediction, and so on, which then yields a strong planning performance. Online, so in real time, one only needs to activate the motion planning head for driving. And in head-to-head comparisons with state-of-the-art academic models, we show that these architectures run 4 times faster than the state-of-the-art, while improving on performance. And equally importantly, this architecture retains introspection and interpretability options, as the auxiliary heads could be optionally exercised, perhaps at a lower frequency, to gain insights into the inner workings of the system. Crucially to our discussion, ParaDrive is built from the ground up to deeply integrate with foundation models. Specifically with ParaDrive, we aren't forced to use foundation models as a wholesale AV stack replacement, but actually we can inject foundation models in a more surgical way. For example, we can have foundation models impact the stack directly in the input space by providing new, more powerful input representations, for example, through video prediction models. Or indirectly, we can impact the stack by shaping input representations via strongly regularizing generative training tasks, such as, again, predicting videos. Or at the output, we can use foundation models at training time as a value functions in a closed-loop training to make the planning head more semantically grounded. And at runtime, we can use foundation models as a high-level reasoning engines, for example, as navigation planners, or we can use them as safety monitors, as I will discuss soon. Importantly, at runtime, foundation models may only have to be run on demand, for example, as part of an anomaly detection systems, or periodically at a much lower than planning frequency, only for difficult scenarios. And I think that such a separation of timescales critically enabled by the parallel architecture will likely be key for the inline deployment of foundation models. And this is also very intuitive. When you drive, typically you don't really pay much attention, but when there is something that is very difficult, you slow down, and then that's when you use your brain and your full cognitive capabilities. That's a little bit what this architecture is replicating. As one example, here we call the large language model part of the ParaDrive architecture at a regular low frequency interval as a navigation planner to help us reason about construction zones. Specifically in this setting, the LLM recognizes the traffic cones and outputs a behavioral plan whereby the vehicle is directed to change lane to the left to bypass the construction area. Once passing all the traffic cones, the LLM then decides to change lane back to the right in order to carry out the right turn at the next intersection following the route plan. So navigation planning is typically a difficult capability to get right. So it's nice to see how LLMs can be effectively leveraged for this task. So finally, let me quickly conclude by talking about safety. Rightly so, there are a lot of concerns in the community about the use of foundation models in safety critical applications, for example, to their notorious occasional hallucinations. And while these are certainly valid concerns, it's important to recognize that foundation models are not black magic. They are fundamentally data-driven models, albeit large ones, for which we have several tools to keep them in check. Our core strategy for assuring safety with foundation models involve three key directions. First, quantifying the uncertainty of the output of foundation models. Second, building runtime monitors and guardrails to keep foundation models in check. And third, developing safety KPIs and the rigorous testing regimen for foundation models. And I couldn't spend an entire talk discussing these topics, but here what I want to do is to instead discuss in some detail the opportunity offered by foundation models to actually help with building a safety case for autonomous vehicles. Specifically, something that has been somewhat overlooked so far is that foundation models have the potential to improve overall safety. Those familiar with the safety engineering V model, we recognize two key aspects of building a safe system: the design phase and the validation phase. The common sense knowledge and reasoning capabilities of foundation models provide opportunities to aid in both aspects. On the design side, foundation models can become part of a safer AV system by serving as effective runtime monitors for key AI components. And on the validation side, foundation models can be used to auto-label operational design domains from the raw data, measure the safety of a given behavior, and aid in generating safety-critical scenarios for testing, as I shown before. To make things more concrete, let's discuss in more detail the topic of foundation models for building runtime monitors to detect anomalies and trigger contingency plans. In particular, I want to focus on a specific class of anomaly, which I refer to as semantic anomalies. Concretely, let's take a look at this video from a Tesla display. At first glance, the visualization looks completely nonsensical, but after a few more seconds, and especially after we see what the actual scene looks like, basically there is a track with traffic lights on top, we as humans have no trouble understanding what's going on. So basically the detection system is fooled and is generated this endless sequence of traffic lights, recognizing them as legal traffic lights by mistake. Or here is another example, this time of a stop sign on a billboard causing trouble, namely causing a ghost brake from a Tesla vehicle, which is an inconvenience for sure, but also a safety hazard. The interesting thing about these cases is that at the object level, you can't really say that, for example, the detector is malfunctioning. For example, on the right example, we are correct, the detector is correctly detecting a stop sign. We call this class of problems as semantic anomalies. That is, edge cases unseen in the training data and caused by an unusual and tricky combination of in-distribution objects. The semantic anomalies induce system-level failures, for example, ghost-breaking events. And while it may be difficult for system designers to foresee all of these cases, the key idea is that a little bit of additional contextual understanding is all that an autonomous vehicle will need in order to detect them. And for this, we turn again to the merging capabilities of large language models. Here we have recreated the first scenario in the car driving simulator, and we can see that the AV is misled by the traffic light on the track, stopping in the middle of the road. So the question is, can we anticipate this before it happens? So we explored the idea of using a general purpose open vocabulary object detector to parse the scene, which finds, among other detections, that a truck carrying a traffic light is part of the scene. We use this information with an input prompt template, which describes the task, as well as includes a few short examples informing the LLM about what factors to consider when detecting anomalies. And running this prompt through the large language model, we receive an output with some excerpts shown here on the right. And we see that in this case, the LLM has assessed the scene contents, deeming some objects such as trees to be no cause for alarm, but indicating that, indeed, the truck carrying a traffic light is an anomaly worth flagging. In addition to classifying these scenarios as anomalous, the large language model also hypothesizes the way it could negatively impact policy behavior. For example, if you can read, the output of the LLM says that this traffic light on a truck could deceive the vehicle into interpreting the traffic light as a legal traffic signal. So this is quite interesting and intriguing that we can get this sort of explanation as well. Now, of course, inference of LLM in real time is typically relatively slow. In more recent work, we have investigated how to make this approach extremely fast by using LLM embeddings for anomaly detection. And with this improvement, we can now run this anomaly detector in real time at 15 hertz. And we also have been flying this anomaly detector on a quadrato platform in my lab at Stanford. So let me conclude by saying that foundation models, through their generalization capabilities, in principle, since they have been trained at internet scale, they have seen everything. So for them, nothing is out of distribution. They provide a lot of opportunities to empower any AV program through their long-tail generalization capabilities. And crucially, as I just mentioned, foundation models provide opportunities to empower the full AV program from offline processes all the way to the online AV stack. This is a very important point that sometimes is missed. Now, I haven't had the time to discuss it today, but of course, there are different types of foundation models, including video foundation models, such as video prediction models, and multimodal large language models. These are two prominent foundation models for the AV tasks. They have complementary strengths, and there are a lot of opportunities to integrate them, unify them, and deploy them into an AV program. Now, in terms of using foundation models for the online AV stack, of course, one way to do it would be to replace the wholesale, replace completely the stack with a foundation model. But I think a parallel architecture provides key opportunities to embed foundation models in a bit more surgical way within a stack, in a way that basically we harness their main capabilities, like, for example, word modeling capabilities and reasoning capabilities, and also avoiding their main drawbacks, for example, the fact that they're typically quite slow at inference time. And finally, for safety, foundation models are not black magic. The automotive industry has been feeding deep learning models in autonomous vehicles for a while now. So we have a lot of strategies to confidently deploy them. But at the same time, foundation models provide key opportunity to improve the safety of autonomous vehicles. I provide an example, for example, through the lens of semantic runtime monitors. So we stop it here, and I'll be happy to answer any questions you might have.
Great, thank you so much.
Acknowledgement to my groups, both at Stanford and NVIDIA.
Sure, thank you. Yeah, so probably I'll start with the question about the visual model versus the language model, right? The visual model seems to have the advantage of construct a model of the world, understanding physics, etc. Or language model more at the symbolic logic, etc. Right? Can you give us a little bit more about how do you see the two can be combined in a synergistic way to actually solve the AV problem?
Yeah, so for example, the parallel architecture provides a good framework to think about this very important question. So here, the argument is that if you can predict the full scene for several seconds in the future, it means that the model has achieved a very detailed and accurate representation of the world. And so in this if you buy this argument, it means that the video prediction models provide the ultimate world modeling capability that can be used then to build a planning head on top. So, for example, in the context of paradigm, instead of using a BV representation that is becoming quite a relatively common representation, you could actually use a backbone that comes from the video prediction model. At the same time, multimodal large language models provide a complementary skills in terms of contextual and semantic reasoning. So they could be used in parallel or downstream a video prediction model to reason in a more nuanced way about corner cases. Now, these models, as I mentioned in my talk, tend to be quite large. But I would say that it's becoming increasingly possible to deploy models in the, say, 1 billion to 2 billion parameters range on embedded platforms, at least automotive grade platforms. So it requires work, but I think we have a path forward.
Cool. So second one relate to this architecture design question there, right? From one side, you mentioned that the search space is vast, right? So much possible combination in this, right? Here, let me ask maybe one specific question. Dan Kahneman have been talking about this system one thinking and system two thinking in one's brain. I think humans are just amazing in switching between the system one and system two very smoothly. Given the context, we'll very quickly adjust our attention level, etc. This, right? So in this deployment of this hybrid architecture that you are developing here, how do you see the two switch back and forth between this?
So, well, first of all, I'm not familiar with this system one and system two concept. But if I understand it correctly, I think is what I've been talking about is somewhat related in the sense that I think one of the key advantages of a parallel architecture is to allow this paradigm of fast and slow reasoning with multiple models, whereby at a lower frequency or even on demand, you may want to query these larger models in order to reason about those cases that are particularly difficult. Of course, to go straight on the road on a highway, you don't need a foundation model. Actually, we can already do it today with much more classical models. What these models really buy you is the long tail generalization. And so that's why, and in a way, this kind of complementarity between more basic models and more nuanced models at different time scales seem to have resemblance to the concept you just mentioned.
Oh, thanks. Yeah, maybe then we'll move to the first part, the offline application, particularly on generating the meaningful simulation, right? So the tool seems really powerful. Now you can just literally describe the situation. It generates the video for you here, right? So one thing I want to let you comment on the role of simulation in the whole development here, right? So one side is what type of scenario and how many scenario we need to generate on this, right? Of course, the edge case is infinite. We can always generate additional more and more scenario. These two create make it much more efficient in that, right? But the other side is when will the industry or the society accept simulation as a valid tool to prove to a quite high degree that this model works on this, right? So on this, what do you see the role of simulation evolve in the whole setting?
So far, simulation of course, simulation is what they used, but the majority of the simulation work relies on one of the simplest but very effective forms of simulation that is basically log replay. So replaying an AV stack over logs that have been recorded by some test vehicle. And it has been traditionally very hard to go beyond that because of the sim-to-real gap, both in terms of sensor simulation and simulation of behaviors from the agents agents on the road. So the two key equations that have been a bottleneck traditionally have been that of realism, and then, of course, that of coverage, how well, which is related to realism, how well we can cover all possible corner cases. I don't think there is a silver bullet approach here. The angle that I was mentioning in my talk is that, at least for realism, language provides a bridge to ground the generation into police reports, which is a strong regularizing signal in terms of getting something realistic. And then you can make a lot of variations of those scenarios. So at least that helps with the realism. And then since, of course, you can think how much data there is in terms of police reports, insurance data, they probably will help big time in terms of addressing the question of coverage. And then regarding when people will accept simulation, again, we are not building a case in a vacuum. So today, if, for example, you want to validate an automated emergency braking system, there are well-established tools and pipelines and protocols to acquire the data and then assess the mean time between failure in terms of FP and FN for your safety feature. That will be something very similar to what we, so simulation basically will be complementing, I would say, as opposed to completely substituting those pipelines and protocols that are well established. But equally importantly, simulation, beyond playing the role of a testing and validation tool, which is very important, hopefully very soon will allow us to provide an environment for training that so far hasn't really happened because of the sim to real gap that I mentioned before. But in the past couple of years, with advances in neural rendering and behavioral simulation and targeted generation, as I mentioned in this talk, we are very close to actually use a simulation for training in a purposeful way.
Nice. Oh, thank you. Yeah. Then let's move to the last module. Is on the safety part, right? You mentioned there's the core as the foundational model, but you put 3 layers of protection there: the uncertainty, the runtime monitoring, then the rigorous testing in the form of KPI, right? But you didn't have much time to describe this a little bit. So can you elaborate maybe one of the 3? So give a little bit more detail on this.
Yeah, so I think a couple of things we're working on is uncertainty quantification. So basically to have a mechanism for the foundation model to communicate its level of uncertainty about its generated output, so that if the model is uncertain, can communicate that uncertainty in an actionable way. And so there is a question of how you communicate that uncertainty, how you represent that uncertainty, and how you calibrate that uncertainty. And there are different things that you can do. For example, here in the slide, I mentioned a statistical technique that is referred to conformal prediction. There are other techniques as well. So that's an important area of research. The other one is, of course, how you can bound the generation capabilities of the model. So, for example, in the case of AV, of course, we know that autonomous vehicles should, respect traffic laws, and they should abide by the laws of physics. So there are different ways where you can inject this kind of rules through symbolic reasoning in the generation process, so that you constrain it in a way that at least you avoid the most nonsensical hallucination that might actually become safety risks. So these are just 2 examples, but there are many more.
That's great. Oh, thank you. Last question from me. I'll encourage people to continue to put questions and thoughts into the chat. The last one, maybe a broader question there, is to look at the knowledge exchange between the industry and the academics here, right? You happen to be striding both sphere here, right? I'd love to see how, even before the foundational model, we already see a kind of a gap between the academic side versus the industry side. Like, what's the competitive advantage, say, academics has, given this large data, large computing that this industry has? With the foundational model, this discussion becomes even more dramatic here, right? So what do you see as the both the each side contribution, but also the knowledge exchange between the industry sphere and the academic sphere here?
Well, so I think that if we talk about scaling these models or adding modalities to these models, that's something very difficult to do for academia for 2 reasons. One, because these models require a huge amount of data, diverse data. Some of it can be simulated, but at the end of the day, you still need to have real data, and that is not typically something you have in academia. And 2, to train these models require a lot of resources. Like, for example, at NVIDIA, the models that we use for video prediction and language modeling leverage parallel efforts in building this model at scale. Because even for NVIDIA, building this model is very expensive. You cannot build too many of them. So that's definitely a setting where universities should not try to, I think, compete with the industry. On the other hand, a lot of ideas are still generated by academia. So, for example, a lot of ideas related to how to optimize the inference speeds for these language models, or how to curtail their negative effects, such as hallucinations. All of these are things that do not require massive investments. They actually require massive brains that I would say we still have in academia. So I still see a future where there is a lot of complementarity between the two. And I observe it all the time, even in my work in video. We routinely inject in our work ideas that have been generated by academia.
Great, yeah.
Sometimes they're pitched in a competition with each other. I think it's useful to reason about what are you best equipped to do, and then do that. Of course, competing with, say, Google on building the next generation LLM might be a little bit of a losing battle. You're better done either a big organization or, for example, through an open source type of framework.
Right. Thank you, Marco. Now give it to John for the audience question. Yeah.
Marco, thank you so much. We had a number of interesting questions pop up, particularly toward the end. And just to let you know, we're going to share this chat file with you after.
Okay, great.
So you'll be able to study them in detail.
And you have my contact. So if anyone has any questions, they are welcome to reach out to me directly.
You bet. Thank you for that.
I'll do my best to reply to everyone.
I want to first turn to a question from Gil Pratt, and if I may, maybe I'll just ask Gil to ask this question directly. Gil, of course, is the chief scientist at Toyota and the CEO of the Toyota Research Institute. Gil, why don't you go ahead and ask directly?
Yeah, thank you so much. Hi, very, very nice to see you, and fantastic work as usual. I was very curious about this nature of driving, where the human beings that are driving other cars are like us. And as we think about our behavior driving, we're kind of having a theory of mind of how we predict other drivers are going to react to us and how we will react to them. It's sort of a very bi-directional loop. Is there any work in your lab in kind of trying to explicitly model other drivers? So, rather than just thinking of it as a black box, having a theory of mind of human beings by trying to replicate human driving behavior?
Yeah, so there are, I think, two components to this question. So first of all, to what extent one wants to explicitly model the decision-making process on the other agents on the road. And if you do so, to what extent you want to resort to black box data-driven models versus something that have some inductive biases in terms of what a human might do, for example, being a rational or bounded rational person. So I would say that traditionally, the policy learning approach is to actually explicitly model the other agents on the road, basically through a trajectory forecasting module that can be more or less sophisticated and more or less combined with the classical prediction schemes. And even though these days, I think that there is quite a bit of interest to only implicitly encode the action-reaction process directly through by learning a policy, for example, through IL, through imitation learning, through some reinforcement learning. That said, still trajectory forecasting is important, for example, in terms, at least, for example, for the purposes of simulation, to simulate the other agents on the road. And in that context, I would say that historically, that field started with more of a theory of mind approach. For example, inference reinforcement learning type of approaches, whereby they were, the idea was to model the human as a rational being trying to optimize a function, and then the goal was basically to futurize that function and then learn it from data. Historically, though, the trend has been to go more toward black box models, including in my lab. One, because they actually prove to work a bit better. Two, they're a bit easier to use. And three, they scale better with data. Now, an argument could be made that also inverse reinforcement learning can scale well with data if you futurize your cost function with deep learned features. But if you do that, at that point, you just go with a black box model. So
Okay.
a long answer to say that, no, in my lab, actually, we are not really using zero-minded approaches to model other agents on the road, neither for on-vehicle policy learning nor for simulation. And I will say that in that, I'm quite aligned with the rest of the community. Not to say that zero-minded approaches are not useful, just maybe lack of bandwidth, and I haven't seen a clear case yet that they might provide big gains for whatever use case you have in mind.
Okay, thank you so much.
Thank you, Gil. It has been interesting how there's been some like gaming of autonomous vehicles, if you will, by people who recognize they're dealing with an autonomous vehicle and sort of jump in front of it or try to get the vehicle to misbehave. So that's, I think, sort of packed into Gil's question. So Marco, there was a whole conversation around energy consumption of autonomous computing. And I wonder if you have reflections on that topic.
Yeah, I mean, this is a little bit outside my domain of expertise. The only thing that I can say, but again, I'm by no means an expert on this topic, is that, of course, to address this question, one should consider the full life cycle of a system. So it is true that training these models incur high costs, including environmental cost. But these models, actually, by definition, being foundational, can be applied and fine-tuned to many different use cases. AV is one, but then you have also enterprise applications, browsers, chatbots. So basically, the cost can be amortized over many different applications. And of course, the other dimension is that these models hopefully improve the efficiency of existing systems, including mobility. So even though upfront you might pay significant environmental cost to train these models, maybe over the lifetime you may be better off because you have more efficient driving and therefore you consume less gasoline if you have an internally combustion engine or you have a minor electric grid. So I don't have the numbers, but I think that if you consider how much this model can be amortized over multiple applications and how they can be actually the negative externalities can be recouped over the full lifetime of the system, I think this is conceivable that in the end we might be better off. But again, one should run the numbers. I haven't done that, so as a scientist, I don't want to speculate further.
Fair enough. But the main point would be one of the things that these foundational models enable is a sort of a high upfront cost, if you will, in terms of the training and development of the model. But then once the model is built, they can actually be quite efficient moving forward from an energy perspective.
That, and also used because they're foundational, foundation, they can be used in many different applications. So you don't have to build a new foundation model for every single application by definition. So hopefully that might quell a little bit the right concern about the environmental impact of this race toward building an increasingly larger foundation model.
Excellent. So several of the questions moved, I would say, from the technical side to some of perhaps the social dimension of autonomous mobility, including questions about sort of the business model. So Jane Chu, for example, asked an interesting question about, do you see a kind of distinction in the rollout of the personally owned autonomous vehicle versus, say, the fleet of robo-taxis versus, say, a fleet of robo-shuttles or more like public transport type enabled autonomous mobility? I know this is outside of your core focus, but we're curious if you have thoughts on that.
I mean, definitely the industry has seen a dramatic shift in the past 3-4 years, right? So a decade ago, the main focus, I would say, was more on full autonomy, also referred to as a level 4 autonomy. These days, I would say the main focus is more on semi-automation, so basically advanced driver assistance systems, or referred to as L2 plus, L2 plus plus. There are different nuances there. And a lot of companies either are fully focused on L2 plus plus, or they have been shifting their focus toward L2 plus plus for a couple of reasons. One, because these are basically more advanced driver assistance systems, so they're targeting the consumer vehicles. So the business case is much clearer, and there is a much clearer path to revenue and profitability in the short term. And I will claim that 2025, 2026 at the latest, but I will say 2025 is the year where very sophisticated advanced driver assistance systems that provide address-to-address services are going to be productized at a massive scale throughout the world. China now has an extremely strong program, and of course the United States. So profitability, I mean, even for companies like Google and NVIDIA, spending billions per year on this technology becomes problematic. And the second is purely technical. As I argued, but of course I'm not the only one, the new way of architecting autonomous vehicles is increasingly more data hungry. And you need the data at a massive scale throughout the world. So if you have a chance to deploy your stack, maybe not super sophisticated, on millions of vehicles throughout the world, basically those are for free vehicles that can generate data for you and now improve your models to go to the next step, which is that of full autonomy. So I think there has been a repositioning of many companies toward more L2 plus, L2 plus plus use cases, both from a business standpoint, but a technology standpoint that will help the business standpoint in the long run, if it makes sense.
Excellent. Thank you.
Great. Yeah. Sorry, to really cut the such interesting conversations. Time is up at 1 o'clock. Yeah, I think Marco, this is such a dynamic kind of scene going on there, right? Hopefully, in 6 months' time, we should invite you again to update what's the latest.
I would love that.
Right.
And see
So everybody, please join me. Thank Professor Michael for the presentation.
So I think the main takeaway is that I don't know exactly what the killer app for foundation models for autonomous vehicle is, but there are so many opportunities that I'm ready to bet that they will stick until in some of the aspects of an AV program.
Indeed. Yeah. Great. Thanks, everybody. Have a good weekend and see you next week.